the University of Bristol, who speaks on L-functions. So please.
Thanks, Mel. Great. So yeah, it's my pleasure to be speaking today. So this is my title, and I'll be talking today about extreme values and questions in rare events, predominantly in terms of Riemann zeta. In the interest of being concise, I think it's wise to focus on an L function. So let's choose zeta. And before I forget, this is work that is in collaboration with these authors, in particular Louis Pierre is speaking immediately after me, and so I suspect there'll be some common themes in what we'll talk about. The results are different. So as an overview as to the types of problems that I want to focus on in this talk, this first question here is exactly an extreme question. It's a question about what is the largest value of the zeta function. We're positioning ourselves actually at a random point, but just think about being some sort of tall point, fixed, and then looking at a small window around there. What is the maximum value? Can we describe it? Can we capture it numerically? Questions along those lines. A natural generalization would be, can we stretch or even contract the window? Can you also capture these what the behavior should be? Does it differ from what I'm saying is a short interval, this first case? Yes, can we capture that numerically? Questions along those lines. And then finally, maybe a priori, if you've not seen these things before, the third topic in green maybe looks out of left field, but there's been a considerable amount of work and very productive work in comparing and modelling the Riemann zeta function in various ways, but in particular here by a random matrix polynomial. And so there's a natural question there you can ask, what is the maximum value in some arc on the circle of this particular characteristic polynomial? So that's sort of contextualizing what I'm talking about. Okay, but first a bit of notation just to set the scene. So as I said, zeta is pushed to the foreground. You could rephrase these questions for more general L functions. But here, the Riemann zeta function, you can see from my cartoon, where we have this Dirichlet series to the right of 1, and otherwise extended to the complex plane with a simple pole. We have some simple zeros, there's no points for those, but the location of the non-trivial zeros is the subject of the Riemann hypothesis, and the conjecture is they all lie on this critical line with real part of S equal to 1/2. So there's many very interesting avenues one could pursue, so let me focus our attention to the moments. So there's a very long-standing conjecture which says that zeta on its critical line, these are the 2 beta moments. Here the moment parameter is 2 beta. The long-standing conjecture says that this should should grow logarithmically in the height t, where log t to the beta squared should be the leading order behavior. And then this leading order coefficient, which traditionally is separated into 2 parts. And I could say a lot more about it, but I think it's largely beyond the scope of the talk. But I do want to highlight the presence of that leading order coefficient. So this conjecture is known to be true. Okay, beta equals 0 is trivial, but the second and the fourth moment, due to Hardy, Littlewood, and Ingham respectively. And we do have a precise, when I say precise, I mean an identification of this coefficient for the 6th and the 8th moments due to Connery and Gosch and Connery and Gonick. And so some information here, A sub beta is capturing some arithmetic information, and C sub beta I'm going to leave to one side for the time being. There are good, when I say good, I mean of this correct shape, lower bounds and upper bounds, and here's a collection of authors, for the lower bound, and then these for the upper bound, but the coefficient remains out of reach for now. So even though we only have concretely the first 2 non-trivial integer moments, we do have a CLT. So we have a central limit theorem, even though we don't have a good handle on all the moments. So this is even without assuming the Riemann hypothesis. So here's the formal statement, but the headline is just that the real part of the logarithm of zeta behaves like a centered Gaussian with this particular variance here. Okay, so that's sort of the 2 key points of zeta I want to highlight, the moments and the central limit theorem. So to pivot momentarily, let's go into random matrix theory. And again, I just need some key properties. So the relevant group it turns out to consider is the unitary group. So capital N here is my matrix size. And the property for these matrices is that their inverse is their conjugate transpose. That forces the eigenvalues of these matrices to lie in the unit circle in the complex plane. So here's a realization of a particular matrix. And so naturally we get such a factorization of the characteristic polynomial. And also explains why I'm writing my polynomial variable in this form. It acts naturally in the unit circle. Okay, so just like we did with Zeta, let's interrogate the characteristic polynomial in the same way. So let's look at the moments. So these were computed by Keating and Snaith 20 years ago now. And we have everything we could ever want here. So the range where this integral is well defined is exactly when the real part of 2 beta is away from -1. So, so the only place where this is well defined, we have all the information. So leading order or subleading, we have a completely closed formula. The eagle-eyed amongst you might spot that there's no theta, there's no position on the circle dependence on the right-hand side. And that's all down to there's a rotation and variance in the measure. So you wouldn't expect theta to appear on the right-hand side. And because we have all the information, in particular, we have the leading order. And so these moments grow like the matrix size to the power beta squared, with a particular coefficient that's completely identifiable as this ratio of branch G functions. And one of the motivations for computing these moments was to produce a central limit theorem. And again, here's the formal statement, but the headline is that the real part of the log, just like we have for Zeta, the real part of the log of the characteristic polynomial is a centered Gaussian with this particular variance. So bringing these two storylines together, this is just to summarize these two. On the left, we have random matrix theory, on the right hand, we have Zeta. And we compare the moments, or if we compare the central limit theorem statements, we're led to the dictionary that matrix size n, if we're going to model Zeta using random matrix theory, the matrix size n should be compared to a logarithmic height t. So that's some information we've gleaned, but also you could infer other information. For example, from the central limit theorem here for Zeta, we learn that on average, or typically, log of Zeta is size square root log t. This is the sort of the opposite question to what I was interested in at the start of the talk, because that was an extreme event. This is an on average event. So what about more extreme questions? So for example, if you look through the literature, you might find that the maximum in what I'm going to call a long range, because capital T, this height, is typically very big. So this is a long range maximum. This is something that has been studied, but such problems are actually theoretically very difficult. And in fact, we're not even, as a community, there's no necessary consensus on what necessarily this maximum should be. So you might want to investigate numerically. But actually, again, this is very difficult. This is a very large haystack and a very small needle. This is an extreme event and a very long range. So let's make the problem a bit more tractable. Let's make our haystack smaller and actually make our haystack random. I'll stop the analogy now. So this is shorter ranges. This is the focus of the Fyodor-Hierry-Keating conjectures, and I'll just abbreviate this to FHK henceforth. I think you'll hear a lot more about this in the subsequent talk to mine, but let me at least just give the statements. So this is, I'm going to choose a point randomly, it's my cartoon on the right-hand side. So in the long range, instead of asking a question of the maximum of this whole range, I'm going to pick a point randomly inside the range and look at a small window. What's the maximum on this small window? Here it's at length 2 pi. And the conjecture, the FHK conjecture, tells us actually a lot of information. It's exceedingly precise. So we have leading order like log t, and this correction like log. I have a subscript here, I mean iterate the log. So log t to the power 3/4. And then the left-hand side is random. My t was chosen randomly. So the randomness is buried in this e to the y term. And I think you'll hear a lot more about that in the next talk. And using the dictionary, actually the story goes the other way around. So the random matrix theory informs Zeta here, but I've written it second for the sake of the talk. So using the dictionary here, you match up n with log t and create this conjecture. So this is the random matrix form of the conjecture. So this sort of addresses the first extreme conjecture that I had at the start of my talk. This is some fixed range that's not growing with t, and here is what the maximum should look like. So there's been a lot of work done to understand both of these numeric, the number theoretic and the random matrix theory conjectures. So I'll let you read the series of authors on the slide, but let me just pick out that from the Zeta range, this third bullet point is the strongest. And so this is work of Argan, Bourgade and Vasseville, which actually gives information exactly on this random aspect of the maximum conjecture. Okay, so that was sort of addressing the first range, but what about if we let our window that we're looking over grow or decay? So this is intermediate regimes. And so Argan, Bourgade and Vasseville showed that if we let our intervals grow in this sense, so either log to some positive power theta or even a negative power theta, you can let them decay, then we actually do get a different answer. So as before, sorry for going back, but as before, our leading would be like log t to the power 1. You can see here that if theta is different from 1, you really do get a different leading order behavior, which means that we have to sort of create a refinement of the FA to K conjecture if we're looking at different lengths of windows. So here is the refinement that those authors proposed. So this is in the range where our window is growing, getting bigger. And so you see the right leading order, and then we get a different sub-leading order here, so a particular power. And let me just comment briefly that actually we can, this is for fixed theta, but there is work in allowing theta to vary and sort of interpolating between the order 1 range and the range growing with t. So that's work of Argan, Dubak and Hartung. So are we able to leverage the preciseness of these conjectures numerically? Can we see this behavior numerically? And the answer is yes, and really in part thanks to how exactly precise these statements are. So let me walk through a couple of the assumptions we use in order to create these numerics. So we're interested in the behavior of this stochastic process. So this t here is random, it's chosen uniformly from this large range, and I'm going to pick a particular interval. So my interval, these are always for positive theta, so my intervals look like this. And then I make at least 2 assumptions. So firstly, and you can actually justify this theoretically, you're fine to discretize. So instead of looking over a continuous interval, you can actually just look over the maximum on a discrete set of points. I'm going to bury the details here, and you can define this discrete set H, and it's related to the number of zeros in the interval. So there's the assumption 1 is that you can go from a continuous to a discrete set. And the second assumption is that the maximum on each of these discrete points, the variables there, they're independent. And so you could have more of a conversation about how legit this assumption is, but it works enough for the numerics. Okay, so just a small hint at the calculations. You can see here so we want to understand the probability, say, that the maximum over this window is greater than this is the leading order, this predicted leading order. So you want to show this probability is small. So to go from this equality, I would just apply to log to both sides of the event in question, so nothing's happened there. And then I want to invoke the 2 assumptions. So here is my maximum of, say here, log zeta, and this is the predicted leading order. I'm going to apply the discretization and the independence assumption to essentially move out the max and pull it into a power here. So this is just the number of points that I'm discretizing over. And now what do we have? We have a question of the log of zeta, what's the probability it's bigger than some value? And I highlighted earlier that we have the Selberg central limit theorem. So Selberg says that log zeta should be like a Gaussian with a variance that's kind of like a half log t. So can we just model this probability with a Gaussian? And you'd see that so Z here is the standard Gaussian, and the size of this right-hand side would have to obey this property. So can we just feed that into numerics? And so again, I'm sweeping a lot of the finer details under the rug, but what does this deliver you? Well, it delivers you this graph here. And this is not the final slide of my talk, because even before I explain the picture, you see that there's a discrepancy at the end here. This doesn't look brilliant. So let me explain this. So the x-axis here is for theta growing. So at the leftmost, this is for order 1 window, and the rightmost, this is for a window of length, essentially log cubed t. And t here is 10 to the 7th. So if you've seen any sort of Zeta numerics, this is in the foothills. We're nowhere near the glorious sort of mountain tops that people can get to. This is very low down. And this orange line is the conjecture. So we were hoping that this orange line should match this red line here. What is the red line? Well, the red line is just the mean of each of these realizations. So you take here, I think 500 attempts around 10 to the 7, and look at your discrete window around there. What is the maximum? And that's this range here. So i.e. yellow line should be matching red line. Something's gone wrong. So what went wrong? Well, what went wrong is that we're trying to apply Selberg. So we considered the probability that log of zeta being greater than here, and we just modeled this with a Gaussian. And so assuming that Selberg still holds. And it turns out this is no longer true at this sort of level. So the statement here is Selberg. So for a fixed real number, it's certainly true that log of zeta being greater than some essentially position that's essentially the standard deviation, that certainly is Gaussian. But you'll see that this right-hand side is essentially order root log t, but we're asking the question something quadratically bigger than that. What is the probability this is greater than log t? So you tend to find a conjecture from Razaville from about a decade ago, which is exactly sort of the regime that we're after. So again, the precise details of what this conjecture said don't really matter, but let me just say, so this Z now is not real. Now it's the right sort of size that we want. It's root log t. So in total, this here is order log t. And so what do you get at this range? Well, it's sort of Gaussian, but you have a multiplicative factor. And what should this multiplicative factor be under the conjecture? Well, it's the leading order coefficient in the moments, where I introduced quite a few slides ago now. So the precise details as to why this should happen, again, I'm going to, beyond the scope of what I want to talk about, but we can add these into our numerics. So you can adapt such a question into numerics, and you get a graph like this. So again, I've slightly squished the graph, so maybe it looks slightly not, this yellow line doesn't look as dramatically bad as it did in the previous graph, but that's just perspective. But here again, what you can see is that we're incorporating the large deviations to Selberg into the numerics here, and that's just this blue line. So you can see again, this is 10 to the 7. This is extremely low down. This is entirely sort of the power of these conjectures, that even sort of this low down the critical line, you can still access such extreme values. It's a difficult thing, difficult needles to find in haystacks, but exactly because the conjecture is so precise, and we even go down to like these fluctuating terms, you can capture such behavior. So let me just sort of pop back here for a second, because I want to make a comment about the random matrix theory aspect as well. So I've been focusing on zeta, but you could ask the same questions for random matrix theory. The difficulty is in random matrix theory is you're confined to the circle. Your characteristic polynomial lives on a unit circle, and so you're confined by periodicity to never pulling your intervals. Your intervals can never grow with t. So you can't sort of directly model these zeta questions using random matrix theory. However, these large deviations questions exactly can be asked. So you could, instead of log of zeta here, you could replace this left-hand side with the log of the characteristic polynomial and ask, is there a large deviation to the Keating and Snaith central limit theorem? And it turns out that what you can do is construct exactly sort of this Razaville type conjecture, And one can prove there exactly that you do get a form like this. So you can show that you tend to a Gaussian, but you have to shift by the appropriate multiplicative factor. And the appropriate multiplicative factor in the random matrix case is exactly you knock off this arithmetic term, because why would you expect arithmetics in random matrix theory? But you still get sort of this other part of the leading order coefficient. So you can show something like this does hold in random matrix theory. So that's just to say that you can create these graphs, you can even sort of go a bit higher up the axis and demonstrate that really these numerics do in fact hold, and we can capture them numerically. So I will stop there. Thank you very much.
Thank you very much. Are there any questions for Emma? I look in the Q&A and I look in the chat. So, Emma, thank you again very much. We will start at in 7 minutes with a brief memorial moment for Lynn Walling, and so that's in about 5 minutes from now. And I will turn everything over at that time to Misha Rudnoff and Sophie Stevens.